Deepfake detectors often fail because they hunt for isolated pixel anomalies, a blurred edge, or an asymmetrical finger. These tools focus on artifacts while ignoring the global physical reality of the scene. The Cesare Protocol, specifically its VITA VQ architecture, moves verification from statistical guessing to rule-based topological auditing. For an organic image, the protocol produces a perfectly symmetrical green heptagon called the VeriGraph, yielding a veracity quotient score of 9.7. Each axis represents a physical law. To remain robust, factors like the optical fingerprint, temporal integrity, and metadata matrix must validate simultaneously. Even when a deepfake looks flawless to a human viewer, its underlying physics are mathematically broken. Synthetic media causes the geometry to fail. The shape collapses where physical logic breaks down, resulting in a jagged red polygon and a VQ score of 2.8. This provides a direct visual mapping of the mathematical manifold, exposing precisely where the data is inconsistent. To isolate synthetic media with this level of precision, we have to look at the mathematical pruning logic that triggers this topological collapse. Standard computer vision models typically rely on graph neural networks to map the relationships between different image features. This process extracts raw visual input into patches via a vision transformer, organizing them into a standard node and edge graph. These graphs operate on dyadic logic, comparing only two specific nodes at a time, looking for a direct relationship between point A and point B. When a dyadic graph tries to model a multi-way interaction, like how light hits a nose, cheek, and eye simultaneously, it has to create a separate edge for every possible pair in that group. This results in click expansion loss. The system becomes an inefficient web of isolated fragments, where the unified truth of the scene is buried under the complexity of the pairs. Generative models exploit this fragmentation. They ensure that local pairs, like an eye and the bridge of a nose, appear statistically correct when analyzed in isolation. This leads to semantic tearing. The deepfake fools the dyadic model locally, even while it violates global physical constraints, like the angle of light across the entire face. Dyadic architectures will struggle to catch modern synthetic media because they only verify if the individual pieces look real, rather than checking if they share the same physical origin. Verifying an authentic photograph requires checking multiple physical laws that must hold true simultaneously. On a human face, the specular highlights on the cornea, the scattering of light through the skin, and the cast shadows must all align with a single light source to be valid. VITA VQ replaces biadic pairs with polyadic reasoning. It binds these disparate constraints into unified sets. These sets are visual ensembles. Instead of a line connecting two points, a hyper-edge polytope encapsulates multiple data points across a 3D matrix. This defines a single dependency, where one rule accounts for light, geometry, and texture simultaneously. If a single node within this ensemble contradicts the physical rule, the entire interaction is flagged. Under polyadic reasoning, visual truth is no longer a sum of isolated parts, but a property of the unbroken integrity of the entire environmental set. When the pixels appear flawless to the eye, the hypergraph must rely on deeper forensics to find a contradiction. Generative models leave behind mathematical fingerprints in their noise profiles. These profiles deviate from the natural sensor data captured by physical hardware. VITA VQ uses a specific metric called muon delta NS to measure the spectral entropy, or the noise floor, of each hyperedge. Looking at this frequency readout, we can see a smooth, natural baseline, interrupted by a jagged, high-frequency spike. This is a GAN artifact. A spike in muon delta NS creates high entropy within that specific hyperedge. This entropy acts as an alarm, signaling that the data points within the visual ensemble belong to different latent spaces, rather than a single physical capture. Spectral entropy enforces a zero-trust standard. A single frequency anomaly invalidates the entire local physical dependency, no matter how photorealistic the image looks. Traditional neural networks handle errors by adjusting their weights through backpropagation. This often averages out deceptive data rather than removing it. The Cesare Protocol uses the self-correcting delta transformer, or SCDT, as an active reasoning layer. It is built to eliminate error entirely. When the SCDT identifies a high-entropy hyperedge, it triggers the forgetting gate. The SCDT executes a householder orthogonal projection. It uses this geometric operation to deal with the compromised data cluster. Rather than being downgraded, the hyperedge is annihilated and pruned from the topological structure. This cryptographic eraser function prevents synthetic data from polluting the global integrity of the image analysis. By utilizing householder projections for total annihilation, the SCDT ensures the final veracity quotient reflects only uncompromised, physically consistent data. After the SCDT has pruned the deceptive hyperedges, the system calculates the final veracity quotient. The VQ score is the combined weight of the validated hyperedges that survived the pruning process. Here we see the direct mathematical translation of pruning. As parameters left zero out, the VeriGraph right collapses inward on the biometric and optical axes. These collapses isolate the exact forensic failure. Lacking correct subsurface light scattering pulls the biometric axis toward zero. In this authentic reference frame, the unpruned data allows the topology to remain robust and convex. The VeriGraph maps the image's physical truth directly onto a dynamic Riemannian manifold. While this works for static images, the VITA VQ architecture is also built for live continuous time response to visual streams. In the VITA VQ inspector, the Hypergraph topology recalculates instantly as data streams in, providing real-time feedback on local anomalies. The pipeline is complete, from patch extraction and hypergraph construction to entropy pruning and the final geometric score. Defending the integrity of the visual record requires moving past systems that merely mimic statistics and adopting those that enforce rule-based physical verification. The Cesare Protocol provides the cryptographically secure standard needed to defend objective reality in an environment where seeing is no longer believing.